So this is the mini project 3 for Xv6 operating system concepts. Our instructor is Dr. Luis-Jaimes. This is a project done for his class at Florida Polytechnic University. The members of this project, the contributors to this project are Nathan Cader. He wrote the report. Benjamin Voor, that's me. I'm making the video right now. Aidan Guenther, he took care of parts 1 and 2. And Khalee Johnson, who did part 3. I wish we all could have written code, but it was a pretty small project, actually, compared to at least the first two. This project extends the Xv6 operating system to correctly handle null pointer dereferences. In the original Xv6, the first page of memory is mapped and accessible, which means that address hexadecimal 0 does not type as expected. Modern operating systems also always map the first page as invalid to prevent this behavior. The objective of this project is to modify Xv6 so that the null page is always unmapped. Any attempt to dereference a null pointer results in a trap in process termination, and system calls properly validate user pointers before accessing them. These changes are verified using the provided test program test1, test2, test3.c, provided by said instructor luis-jaimes for 2025 fall semester. So to set up, I'm going to just show you my directory here. I'm in mini project 3, Xv6 patched. So now you can see that all the files are here, all the files that you can see here. I've already made QEMU just to have that up and running. Not running, but up. Not up, but made, so that you don't have to load it up. You don't have to make clean and then load it. Wait for that. So if I go to the kernel make file, you can see where Aidan, who was unable to use Perl, so you add Perl in, and you're now able to use Perl. It's kind of outside the project, but I kind of just wanted to mention it. It was one of the things he changed. If you look here, we added test1, test2, test3 to the one of the commands that you can do as a user. So now this is going to show up when you hit ls, and it's going to be one of the things that you can type and use. So preview, make it. I've already made it. So this is going to be a very short loading sequence. As you can see, ls, it pops up. And I can even run it. You can see the output here. You can see that all 3 tests pass. Oh, that's a null dereference. You can't do that. Kill the process, test passed. Same thing, bad dereference, kill the process, test passed. Test case 3, test passed. Control A, X. First file is kernel exec.c. We're going to change size from 0 to page size, and what that's going to do is going to leave the first page unmapped. And we're going to protect that zones 0 to 4095. And if you try to access that, we're going to cause a page fault and kill the process. And this is going to catch null pointer bugs immediately. In the both make files, so user make file and kernel make file, we're going to change the memory location to 0x1000. So 0x1000, sorry, hang on. Sorry, but that was saying goodbye to Thanksgiving family. I don't know, it's pretty late at night. So, where was I? That's right, I'm in user make file. So user make file, go to line 77. I'm going to change for this section start from starting at 0 to starting at the first page. Not a start, 0th and 1. From starting at the 0th page to starting at the first page. I hate saying that, but yeah. So you was going for the. I'm not going to say 0th. I hate that. I don't like saying 0th. We're going to go from starting at the first page to starting at the second page. Otherwise, wrong address. So the linker must know where the code will run so it can generate the correct addresses for jumps in function calls. Since exec.c loads user programs at 0x1000, the linker must compile them for 0x1000. Otherwise, wrong addresses will result in a crash. So entry start, section start equals dot text. So also, yeah, so equals 0x1000. If I go over to proc.c here, we're going to have like 3 things here. So I might as well just scroll down. So P, that being, I scroll up here, P being proc, is going to, its size is going to be 2 times 4096. So page size, that's a constant. It's going to be 4096. So we're going to go double 4096 because the process's address space now spans from 0 to 0x2000, even though the first page is unmapped. If I were to go down here to 94, same thing. We're going to change the stack pointer to double the page size so that the stack has room to go downwards from the top of the memory. And what else are we going to do in this file? We're going to change the instruction pointer. So 95. We're going to change the instruction pointer to go from to start at 0 to start at page size. Why can I not select text with the keyboard? I can only do it with my mouse. So beginning of initcode.s changed from 0 to page size. All right. So 87, 95, R, 95. Now we're going to go into vm.c. Here we were starting at 0, but now we're starting at page size to map the second page rather than the first page, the null page, to physical memory. Same file, different line, 309. This I equals initialization is going to change from 0 to page size. Okay, copy view VM function, copy from second page. This is copy view VM. So this is the function. We're going to change this function to copy from the second page instead of the first page. This ensures that child processes only copy the parent's memory, excluding the null page. This is the test case 3, so this is going to be the part that Khalee did. In fetch int method, we don't want to extend outside of the stack into the code of the program. So kernel syscall.c, right? So we got a process greater than 1 or lesser than 4096. So this is going to be the first page. We're going to return -1. We don't want that. We're going to trap that. So this is line 22 for fetch int, and then fetch string. We're going to do the same thing on line 39. Sorry, 39 is a meme. We're going to do the first page. If it's there, we're going to turn -1. So the problem is that the addresses inside the first 4 kilobytes, 4096 times 1000, 4 times 1024, that's the 4 kilobytes, are never valid user data. Real programs don't keep data there. The OS intentionally marks it invalid. The program fixes this by stopping bad pointers, cases A and B, before Xv6 ever dereferences them. You go to arg pointer function. I think it's the same file. Further down, I'm gonna do this with my mouse here. So it's the same logic. We're just casting I as a unsigned integer. We're casting int I as an unsigned int I integer, and we're saying if it's lesser than 4096 or is greater than or equal to user top, we're going to return -1. So this line 70 marks the boundary between legal user memory and the code or kernel region. If the pointer touches that boundary, it means it points into the code segment where its size might spill into it. The third bad pointer starts inside valid stack memory, but its length goes past the legal range. The program fixes this by checking blocks the entire scenario. PS its user top is declared on line 15, include param dot h as 655,360, or in hexadecimal, it's A0000. That's the end of the user space. What did I do? I did not mean to do that. I'm thinking, yeah, I did Control X because I'm used to Keymail. Control A X. That's not the correct one. Yeah, testing cases. We're gonna uncomment bounds. Uncomment bounds. Um, this. So yeah, let me see the conclusion here. This project required modifying Xv6 to invalidate the null page, update memory logic, update memory layout loading logic, and strengthen. That's grammatically incorrect. And strengthening pointer validation inside system calls. With these changes, Xv6 works like a modern OS when there's null pointer dereferences and incorrect syscall pointers. All three test cases from the provided test program were successfully passed. Have a good day.